Okay, well, thank you so much, and thanks for inviting me here. It's great to be here. My talk was going to be fully twisted bilayer, but because there were 5 talks on, or there's going to be 5 talks on anomalous Hall crystal. I'm just going to give you also a little bit of, I'm not sure if a different perspective, but certainly like half of the talk is going to be about fractional Chern insulators. So this work on twisted bilayer was mostly done by Haoyu, Dumitru, Jonah, and Jabin. And of course, there's many senior collaborators that we had the pleasure of interacting with, especially Zida Song, Dmitry Evtov, Nicolas, Oscar, Alexei, and Roser and Tim's and Georgios group. And Roser will be basically talking about some of these aspects later in the week. So I'll assume full knowledge after a full day of talks on fractional Chern insulators and twisted bilayer. I'll assume full knowledge of all these aspects, especially the anomalous Hall crystals and other states, and just dive right into it. So basically, in the first half, what we're going to try to do is sort of understand, or at least lay the foundations toward understanding an experimental fact in twisted bilayer graphene. And this experimental fact is basically a dichotomy between 2 different types of experiments, one that sees local moments and one that sees itinerant physics. And really this dichotomy was started by experiments here by Andreas' group with local moments and Shahalilani, and of course there's the delocalized electron experiments of Pablo, Dima, Philip, and also Andrea, and he has other people such as Chern insulators, etc. So basically, the moral of the story is really captured in this abstract, which says that the correlated state features seemingly contradictory properties, some associated with itinerant electrons and others associated with localized moments. So how do we understand that? Well, there's a way to derive this kind of dual description. And the way to derive this dual description is to go to the Bister-McDonald model and then to realize that these 2 flat bands per valley per spin don't have a localized description because they're topological. Now, the topology was pointed out early on in this series of papers. There's more papers, but there's only that much space. But there basically was pointed out early on in this series of papers, and has to do really with the fact that there's the wrong symmetry representations at the gamma point. At the gamma point, there's gamma 1, gamma 2 representations. If they were switched with a doublet representation, gamma 3, which sits within the Coulomb breach, then we would be able to build a localized description. So if you take this at face value, you can actually make Vanier states of px plus minus IPY orbitals, which sit on the AA size of twisted bilayer, and these are localized within 0.2 of the Moiré scale. So they're very localized. Their Hamiltonian will be 0, really, and you can ask how much of these flat bands do they encompass, and they encompass 95% of these flat bands. So then you ask, where's the rest of the 5% of the flat bands? These flat bands cannot be fully encompassed by localized states because they are topological, and at the gamma point, the overlap with these localized states has to be 0 because they have the wrong representations. So what's the rest of the 5%? Well, you can derive the model, or you can argue by symmetry. They both lead you to the same result. The remaining states are actually that of untwisted bilayer graphene with a gap between these states of the order of the Bister-McDonald or the continuum model dispersion. So if you take this at face value and you build the basis of what we call C electrons, which carry the topology, so this double vortex carries the topology, it's a 4-component system. This is the heavy fermion 2-component per valley per spin, px plus minus IPY the Hamiltonian is 0, then this is the double vortex Hamiltonian with a small mass. We can put this mass to 0, and then really it will be 2 linear dispersions. And what you can say is, well, this Hamiltonian with just the heavy fermions, which are just flat, plus the double dispersion looks nothing like the continuum model, but the only thing you need to do to make it look like the continuum model is to add a hybridization term, which is not added by hand, it's actually derived, but by symmetry you can immediately understand the hybridization term because these twofold vortex and the heavy fermions have the same representation, so they're going to allow a term which is a constant, and if you add this, you get perfect match with the continuum model. Now, I want to very quickly point out that this is kind of a way to understand bandwidth concentrated Berry curvature. This is actually the opposite limit from the Landau level. And the reason for this is that if I have concentrated Berry curvature at one point, then most of the band has no of the flat bands. This is, not some non-abelian Berry curvature. Most of the band has 0 Berry curvature, and then there's no obstruction to localization. So I can localize most of the band. The only thing that I can't localize, especially if I have a topological band, is the point where the hotspot of the Berry curvature is, but then I can pawn off the topology or the Berry curvature onto a gapless fermion and describe the system as a heavy flat fermion with carries the interaction coupled to a conduction fermion, and this will lead to in the interacting picture, when you take the Coulomb interaction and project into this basis, a generalized Anderson model. The generalized Anderson model for TBG is the following, and again, this is not postulated, it's just derived. You take the Coulomb interaction, project it onto this basis, and you get several terms. The largest term that you get is the Hubbard-U term, and this is only for the F fermions. You get a density interaction between the C and F fermions. You also get a ferromagnetic coupling between some U4 moments of the spins, U4 spins of the light and heavy electrons. And basically, the idea is that this is a large standard scalable problem. It's got, it's a Hubbard term for the F electrons and carries the correlation, and the C electrons are almost linearly dispersive. There's a small mass, which is the continuum model bandwidth, but really they're strongly dispersive and they're weakly correlated carriers. So now you can...
In your paper,
okay.
Your W factor was comparable to U.
Yeah, but that's a density term. It is comparable to the use, but that's the density term, which basically leads to the Hartree shift. So this is not if you're going to do, and I want to get to the FCI, so Rosa's going to explain this more carefully. It's basically you can treat that in mean field. That's a very good point. So basically, if we ignore the FC hybridization, which means that constant term between the F and the C electrons, what happens is that, of course, we can solve the model exactly, and the model has the following properties. First of all, the Hubbard-U needs to be minimized. So this is, for example, at half filling, you polarize the, you split the F electrons, you form Hubbard bands here. There's no hybridization between the F and the C electrons, so there's no level splitting here. And then as you move away from half filling, you're going to fill the C electrons. You see, this is the small bandwidth of the Bristol-McDonald, and you're going to fill the C electrons, and this is what this happens. This is this line here, and as you go towards the Hubbard band, at some point you're going to have a reorganization because the chemical potential, as you fill, goes here, and then it becomes energetically favorable to fill the F electrons at the next filling. So basically, we have two regimes, and this sequence kind of goes in and out. And we have two regimes. You have the regime at integer fillings, which is local moment region, and the regime of mixed valence, which is the charge fluctuation between the F and the C electrons. Now, this is in the zero hybridization problem, as the paper by Gautam Rai and Lawrence Kripa and from Rosa's group will show. One can extend this to the finite hybridization. But working the zero hybridization limit at integer filling, what we find is, and this is related to the W term, Mitch was talking about. Basically, what we find is that you can polarize the F electrons at integer filling, and then this gap is opened by the spin interaction between the F and the C electrons. Now, if you put in the hybridization term, these level crossings open, and you get this type of charge excitations, and then this Hartree shift that the W term gives you basically gives you this asymmetry between electrons, or away from, this is really holes, really away from integer filling, so -1 minus epsilon, -1 plus epsilon here. There was noticed early on by Askang and Bafek, and a lot of the people cited here. So these are the integer filling states, and now you can ask, well, if they're really insulators, how can I test the idea of having these heavy and light particles? Well, there's many ways we can test it. I'm not sure. The Landau-Fan used to be one way we're thinking about it. Now there's probably Oscar is going to talk about it. There's a different perspective on it also. But one way of looking at it is through the Seebeck coefficient, and I think Dmitry Efetov is going to talk about this. Basically, a split gate thermal excitation experiment where you measure the Seebeck coefficient. Now, if you have a graduate student like Dmitry and a postdoc like Howie, they'll tell you that the Seebeck coefficient for electrons is negative and for holes is positive. But then you look at the experiment, and as you go through the phase transition at nu equals to 1, the Seebeck coefficient stays negative. It doesn't go positive. So one way, you can do some theory for this, but the heuristic way that basically the theory leads to understand this, because I don't have time to obviously present the entire theory, is the following. If I just had a mass difference between the light and the heavy electrons, then what I would get is a positive coefficient for the holes away from integer filling a little bit, and a negative one for electrons. And this, the peaks would be asymmetric because of the different mass, but you wouldn't see fully negative Seebeck coefficient. Now, the main idea, which is supported by Foreman's DMFT, which is the IPT approximation that we did, is to compute the lifetime of these particles, because the holes here being the flat band, being the heavy electrons, they're very localized, so they actually won't contribute to transport. And this is not really at zero temperature. So if you put a life asymmetry in the problem in which the lifetime of the electrons is much, much larger than the lifetime of the holes, which comes out of the calculation, you immediately see the fact that you can kill the hole peak and obtain fully negative Seebeck coefficient. So this is the story around integer fillings, away from integer fillings at 1.5, and the reason why I'm showing this is because I want to basically present you some results on superconductivity here. I'm not claiming that we explain superconductivity here, far from it. I'm just claiming that it could be a scenario. So Howie and Dmitry basically did Foreman's DMFT, which is the IPT approximation invented by Antoine George and Gabi Kotliar, I think, which basically interpolates between small u second order self-energy and large u atomic limit. And in this approximation, where you can get actually Kondo physics, what you see is that at high temperatures, you're going to get the Hubbard bands. This is at filling 1.5, for example, and then at some intermediate temperature, you get the incoherent F excitation near the Fermi, and then at even lower temperature, you get a coherent F excitation near Fermi, and the Kondo coherence has been developed. Now, of course, this is just very simple theory. So how do we know whether it could be correct in terms of a modeling perspective? Well, we don't, unless we appeal to Rother, Tim, and San Giorgio's groups, but there's other people that also have looked into this, especially Lenny Bascones, which it's not here. But basically, the moral of the story is that their calculations, I think Rother will basically show, is that you can clearly see in DMFT that there's at integer fillings, Kondo is relevant, and at non-integer fillings, you do get Kondo behavior as you see in T times the susceptibility. Now, just very quickly showing this, there's a lot of other works, including by Shankar's group, by Pierce's group, by Jidasong's group, by Bascones' group, that basically give you the same sort of symmetric state Kondo behavior that I think Rother will be talking about. Now, I want to get very quickly to superconductivity. Again, I don't claim this is the theory of superconductivity here, but it is a scenario where you can understand how this large Hubbard U that exists in the problem can get screened. And on this scenario, you can add different attractive interactions. Electron phonon is certainly one of them, and probably very important, and it was added by Jidasong. But what we did here is just to look at whether the Kondo state can actually screen the Hubbard U. And what we find is that the on-site repulsion is diminished by a factor of 4, but then you get the nearest neighbor attractive interaction of 2 million electron volts in the F channels. So this would be like a pseudo gap. Now what this gives you, so again, I'm not claiming that this is the symmetry. What I'm claiming that this is what you get in this theory, and you could add electron phonon, which are probably very important, and this is what Jidasong did. But basically, what I'm claiming is that in this limit of nearest neighbor attraction, there are 2 representations that are relevant, and these are all either spin triplet intervalley or spin singlet intravalley or intervalley, basically valley triplet. We don't really have SU2 in valley, but the valley triplet, and the lowest superconducting state is actually gapless and triplet. But again, there's many other competing states very close by, some of which was pointed out by Paco, and hence, it's not. This is not a theory of superconductivity. It's basically a scenario of how we can screen the large Hubbard U. Now, the last 3 slides that I wanted to show is how you can incorporate relaxation and strain in this heavy fermion model and the IKS state that Sid and Nick predicted. So basically, what you do is you take these low energy models, which are based on Vafek and Kang in this particular theory, and which are also based on Caceres and Conchino and Luskin and McDonald and Carr papers on ab initio. But basically, what you do is you take these strain and relaxation and project them to the heavy fermion basis, and you ask, are they good representation? And it turns out that you can see the match here. They're an excellent representation, the heavy fermions, in terms of these strain and relaxation. And really, what's really important is that, for example, strain enters by splitting the heavy fermion states. So that's the massive effect of strain. It's just splitting the heavy fermion states. Now, the relaxation enters in this model just as a different chemical potential of the C electrons and the heavy electrons. So it's a very simple, this is a particle symmetry breaking term, and this is a C3 symmetry breaking term. So now I'm not going to go through it, but basically the moral of the story is that once you have this, you can reproduce in one shot Hartree-Fock the remarkable states that Sid and Kwan and Bultnick and Steve Simon and others basically predicted, which is the IKS state, which gives you gapless and nu equals 0, gapless and nu equals -1, with, without relaxation, this would be particle Hall symmetry, but then you add relaxation, it's not, and gapped at -2. And then if you add relaxation, you can also understand very easily the fact that you would get a larger gap at nu equals +2 than at nu equals -2, even though the dispersion is larger in the electron band, bare band, as you can see here, dispersion larger, the actual gap of the insulating state is larger, positive filling than negative filling. So with that, I'm going to conclude the twisted bilayer part and try to give you the perspective on the fractional Chern insulator. And this is really work that has been spearheaded by Jabin and Jonah and Yves Kwan, but of course there's been, Nicolas and my long-term collaborator has been basically running this work. There's new collaborations with Titus Neupert and with Oscar Rafik and Xiaodong, but also with, of course, the ab initio group of Hongming Wen and Quan Sheng, who in Peking. So the moral of the story here, and the gist of what I'm going to tell you, is that we don't, in our view, we don't know very much of what's going on, and I think this is where we differ from the other talks. And I think that it's basically numerics, or at least the theory, is really still trying to reproduce some of the aspects of the experiment. And in TMDs, the only thing we can fully reproduce without, killing it if we introduce band mixing are the 2/3 state, 3/5 state in the first band, just the regular sequence, and everything else is a little bit up in the air. But basically, the moral of the story is that if you look at the FCIs, and this is early work done on actually when we did this work, we did it on Kai-Sun and Shankar's flat band model. We took their Hamiltonian and fractionally filled it. Other people did it on Tang and Wen's flat band model. But basically what you do is you fractionally fill a quasi-flat Chern band, and you look for this threefold degeneracy at filling 1/3, for example. So degeneracy is crucial, but it's not the only thing. What you can see here is n of k, and n of k needs to be basically to not fluctuate a lot. So you can see here fluctuations of less than 10%, or somehow here it's like 15%, but most of them are less than 10%. And this is on small sizes. As you grow, these fluctuations should disappear. You can see this filling 1/3, n of k, occupation number. So you need to look into the fluctuations, and then you need to look into entanglement spectrum and other things to actually point out that it is an FCI state and not just a charge density wave or other things. So in the experiments by Xiaodong and Fine and Xie, Jiashan is basically, they have the TMDs, which I'm not going to show a model because everybody knows them. But basically, the moral of the story is they see magnetization from, minus 1/3 to minus roughly 1.2, 1.3. Okay, so this is the first thing that we should explain, along with the 2/3 state. Magnetization dies at minus minus 1.3, minus 1.4 at 3.8 degrees. So these are the key features of the experiment. Now, when we started getting into this game, there were some models given by the people here, but really there were different types of models, and we didn't know which parameters to use, and we did our own ab initio, and we basically got the same parameters that Di Xiao has. Now, what Di Xiao pointed out, which is the fundamental aspect of these TMDs, is that as you lower the angle, you can't just use the first harmonic model. There's many other harmonics coming in, and you have to use all the harmonics to get a correct representation of the model, which is Landau levels basically for the first 3 bands at least at low angle. So you can't just use the 3-parameter model, even though this is an okay model for 3.8 degrees. It's qualitatively not going to match not going to match the phase transitions or the Chern numbers of the bands at lower angle. So this is a fundamental thing that one needs to take into account when doing these calculations. It's a fundamental thing that Kao and Xiao basically showed. So then what we did is to just take one band per valley system and do hexagonalization. And if you do this, you can obtain sort of the FCI states more or less in, there's a difference between the different sets of parameters. I'm not going to claim one set of parameters is better than the other, but basically the moral of the story is that at -4/3, one band per valley, you get a spin gap and the system looks spin polarized in contradiction with the experiments. Then, if you take two bands per valley, you can immediately see that the band mixing fixes this problem for the Shaw's parameter. So basically what you see is that at -2/3 you have a spin gap, just like the FCI, and -1/3 you basically don't, you either have a FCI, weak FCI, no spin gap almost, or a charge density wave. So there's many competing phases here, just like the experiment, and at -4/3 you again have no spin gap, just like the experiment. So this actually points out the following things, that band mixing is essential. Okay, and this was something that was not only pointed out by us, but there was a lot of other people, and sort of at the same time, Young's group and Emil Berhol's group and Yang Zhang also had papers pointing out that band mixing is essential, because otherwise you can't explain the experiment. So band mixing being essential, then I would expect calculations to be done with band mixing. So let's do calculations with band mixing and look at what happens when you take, for example, the -1 composite Fermi liquid spectrum. So these are our calculations, but we of course agree with one band per valley with the calculations that appear in the literature. And what you see is the following degeneracy. Of course, the gapless state, so it's a finite size degeneracy fitting the Fermi surface. And you see in Landau level degeneracy, this is 2 times, for example, 6. And then you see, for example, in MOT2, it's a little bit split. Okay? But then if you do 2 bands per valley, so this looks like the Landau level, but then if you do 2 bands per valley, that degeneracy is gone. Okay? So band mixing does kill this. Now I'm not claiming, very crucially, that this state is not a composite Fermi, but I'm just claiming that we cannot declare victory by theory for having predicted this state, because band mixing, we know that theories predict not just us, but others, predict that band mixing is important. So, one should look at the effects of band mixing and, at possible other states here, although likely it might be a composite Fermi liquid, and, this is a gapless state. I wouldn't put that much into the degeneracy, but basically we can't use it as an indicator. Now, the other thing that was basically mentioned yesterday, actually, is this experiment at filling -3, which could be interpreted as 2 -3½ non-abelian states. So then, there's certainly the experiment, obviously, you can't argue with the data, the experiment shows something very, very interesting. Now, what I'm saying is the theory, and if you do the theory at -3½, unlike papers in the literature, we do not find a non-abelian state. What we find is that we find the degeneracy of a non-abelian state, but if you look at the fluctuations, they're 60%. Okay? So n of k fluctuation is 60%. It certainly doesn't look like an incompressible state that we showed at the beginning. The other thing is, we looked at some FTIs, and that's not FTIs at low angle, but FTIs at finite, at large angle. And what we see is that you could have FTIs for equal intervalley and intervalley interaction, which is kind of a new thing that wasn't pointed out before. But the bad thing is that the interaction that you need, even though it's equal for intervalley and intravalley, is much lower, of much lower pseudopotential than what you get realistically. Now, in the last 3 minutes, I hope, Andrei, thank you so much, I'm going to show some results on rhombohedral graphene. So these are the data round 1. Now, of course, there's round 2 of data, which the jury's still out on how to explain that. But basically, round 2 is you have some fractions, and then also this was found by several groups, well, 2 groups now, the long group at MIT, and Chalbaud's group at Peking. Now, of course, you know, I'm just gonna go through the slide very quickly, but this is the band structure folded into the Moiré zone, and you can see this flat band here, but you can see it's gapless. Now, some relaxation of orange and black, see, it's not very important for the conduction bands because they're away from the Moiré. So this matches all the, you know, 3 talks that we heard yesterday and 2 talks that we're going to hear today, story about the bands being away from the Moiré. Now, there's 2, and this is actually one way of possibly discerning between different things I'm going to tell you. There's 2 stackings of HBN that are rotated by 180 degrees. One of them basically being the boron side on top of the A side of the pentalayer, one of them being on top of the B side. Now, what was mentioned, what was actually not mentioned yesterday, and what's really important to mention, is that there are several interaction schemes. And actually, this is something that was pointed out by Reddy and Fu in a phenomenological model. That phenomenological particular model gives you the wrong Chern number, but this is the kind of materialization of that model that gives you the correct Chern number. So basically, what happens is that in this band, in this flat band here, which has very little Moiré, you can think of adding the interaction in 2 different ways. If the potential is very small, you can't just project to the flat band. That's just incorrect because you have very small potential and you have, you know, the valence bands, which are actually very strongly Moiré coupled, you know, influencing it. And what you do is to normal order interaction with respect to half filling. We call this the average scheme. Now, the scheme that's used in all the anomalous Hall crystal, we're just going to choose that name that was already talked about yesterday, is the scheme that you project into these bands. So now, you know, there's other things such as, you know, 3D versions of the Coulomb, but the main story is the difference between these 2 interaction schemes. Once the scheme where you basically normal order with respect to charge neutrality, which is the scheme used in twisted bilayer graphene and just in graphene interacting states, that scheme actually has a large Moiré due to the interactions. So let's see the Hartree-Fock results of the 2 schemes. One scheme gives you and these are, you know, several papers that have these interaction schemes. It gives you metal, Chern 1, Chern 0, Chern 1, metal, and Chern 0 here for a range of, this is interaction, this is displacement field. The other stacking, so that's for one stacking. The other stacking gives you Chern 0 in the electron band. So now, what I wanted to show, and basically I'm just going to take 3 more minutes. What I wanted to show is that there's these 2 interaction schemes basically can give sort of different results. Now, whether they're really dependent on parameters needs to be checked, as Yahui basically pointed out. The projection to the conduction band also can give you Chern 0 and Chern 1, which actually I wasn't aware, but for a set of parameters which is in the Parker model, it only gives you metal Chern equals 1 to Chern equals 0. Now, clearly, this is a parameter dependent now, and we're running Hartree-Fock on this model. But the moral of the story is that, and this is something that Senthil was pointing out early on, there seem to be no states, you know, we should expect these stackings to be similar. There seem to be no states with Chern equals 0 only on the electron side. Well, that's actually not true anymore, and this is courtesy of Chalbaud-Luce, which basically sees Chern 0 states and nu equals 1 for some. You know, they just didn't report them because they thought they were not interesting away from the Moiré. Now, what I wanted to last 3 slides show. Sorry. No, but nobody's going to ask questions. So.
not if you keep talking at this speed.
So what I wanted to show is the difference between the Moiré Chern insulator and the anomalous Hall crystal. And this is just the difference in the interaction. Okay, so you can see the Moiré Chern insulator has the phonon collective modes, and this is something that Raquel asked yesterday. Has the phonon collective modes gapped very, very heavily, and then the anomalous crystal has the phonon collective modes gapped a bit weakly just by the Moiré. Lastly, I just want to point out the FCI issue. And there's a massive issue here because, as Yahui showed yesterday, you know, if I just project to the Hartree-Fock band, which I obtained at filling 1, and it's a Chern insulator, I will get an FCI, right? Threefold degeneracy. Looks pretty good in N of K, I didn't show you. Now, the system is gapless to start off with, so projection to the Hartree-Fock band is, in my view, heavily biasing the system. So what you can do is, however, include fluctuations to these bands. And that's a hard problem because now you have to do 3-band ED, which is very, very expensive. And you can't go above 12 sites. You can't go to 15 sites, actually. That's too expensive. So you have to devise new methods. And the methods we devise is to basically do orbital and band restriction, which can basically lead us to 24 sites. Okay? So it's a massive increase of the ED. And here's are the problems with the 1-band ED. 1-band ED gives you, in our case also, a nice fractional Chern insulator, but you start adding fluctuations at filling 2/3 into the next bands, and the Chern insulator gap collapses. This is in the charge neutrality scheme. This is just projection to the bands. You can see that even the degeneracy of the levels changes, the momentum changes. They're at momenta that don't fulfill gap states by the Lieb-Martinschof theorem. Now, one thing you do see is a difference between 1/3 and 2/3 as you add, in this average scheme, where Moiré is important, as you add fluctuations into the other bands, the 2/3 state first increases in strength and then loses out, collapses, whereas the 1/3 state immediately collapses. Last slide, sorry to go here. Last slide, if I didn't convince you enough that 1-band ED is biasing the system, let me just plot the occupation number of the other bands. This is the Hartree-Fock band occupation number. It goes down, and in the as you add fluctuations, and in the limit where the fluctuations are added fully, we claim that the second band basically has a similar occupation as the first band or the other bands. So this is finally my conclusion, and the conclusion is that calculations must include band mixing in all FCA systems. The FCA at 2/3 seems to collapse slowly when fluctuations are taken into account. It's in the low energy Hilbert space, but it collapses. And they suggest that 2/3 is a low energy state, but hopefully not, but perhaps not the ground state. But even at nu equals 1, we have ED that suggests that some Hartree-Fock, as there was a discussion yesterday about whether we should trust Hartree-Fock in Wigner crystals, might not be reliable or might be reliable. And to here, I refer to the beautiful, eloquent discussions by Senthil and Shankar. And there's a massive issue of what the T=0 nature of the 2/3 state is, and ongoing calculations are going for the 3/5 state. So with that, I thank you, and I apologize for taking so much of your time.
All right, we have time for maybe 1 or 2 questions.
Sorry, I have a question about the beginning half of the talk, specifically the decoupled limit of the heavy fermion model.
Yes? Go ahead.
Yeah, on this slide. So, okay, there's a, so one thing is that on the bottom left, it looks like at -4, there are, the filling of F electrons is -3 instead of -4?
So because of the W term, there's a shift. You don't get exactly, so there's a lot of charge fluctuations as you go to -3 and -4. There's a lot more. Because of this W shift, the W term is not exactly U. If it was exactly U, so there's a density term. If it was exactly U, you get exactly 4, etc. 4, 3 to 1. Because of that, you can see how it shifts. You can see that the plateau here is not exactly starting at -1.5. Right? So there's a shift. I wouldn't trust the simple one, linear K heavy fermion model for these large fittings, one would need to add extra terms like K squared or other terms.
Oh, I see. So it's an issue with the cutoff of the C
Yeah,
electrons.
because you go too high. So, when you get there, if I add K squared terms, I would get, a little bit of a different answer here. It doesn't matter at lower, up to -3, it doesn't matter. Once you get there, but, it's a K dot P expansion in the conduction fermion. So once you add the next order terms, you fix that.
So you expect to trust the model close to 0, basically? Before.
Well, no, not close to 0. Between -3 and 0 and +3. So, well, at least, look, I mean, the real question of this model, and, I'm not sure if Oscar is going to touch on it, is if the Hubbard U is as high as, we have it in this model. But that's a derived question. That's a derived Hubbard U. So if it's not as high, then there's a problem with the derivation. We have we need to understand that. If it's a derived model, so if the values are correct that we derived, then if they're not correct, then we need to understand why the system seems to be less correlated then, and what the STM says. Because the STM says it gives a value for Hubbard.
But along these lines, I have another clarification that I was confused about, which is that here it says you ignore the FC hybridization for the decoupled limit, but then on the previous slide it also says that you set the velocity of the C electrons to 0.
Where did I say we said the velocity?
On the bottom left, decoupled model.
No, this is V prime.
Oh,
this is a remnant. This is, I should just delete this. The V prime is something that is an expansion here. In gamma, there's some V prime. This V prime is not this V. That's why it's got a prime, and it's just there to confuse you.
I think let's cut this off. I'm sorry, and move on to the next speaker. Yeah.